We're talking about cause and effect, and really the difference between causal relationships and the different types of relationships that exist between sets of data, independent variables and dependent variables, and maybe some of the reasons behind the correlations that we've been looking at for the last few lessons.
Correct.
So, to begin, we're going to talk about causal relationships. Relationships that exist between an independent variable and a dependent variable that changes in one cause changes in the other.
Yeah.
Okay.
And specifically, that your hypothesis that your independent variable causes your dependent variable, that's the causal relationship. And the order that you chose, independent before dependent, is the correct one.
So we're going to start by investigating an example. And here, this is basically against the vaccine that was developed to fight polio. Investigators in this study looked at the relationship between the incidence of polio and the number of soft drinks that were sold. Okay, so for each week of the year, they tabulated the number of soft drinks that were sold and the number of new polio cases that were reported. And these data points showed a very strong positive correlation. So during the weeks when more soft drinks were sold, there were more new cases of polio. When fewer drinks were sold, we had fewer cases of polio. Yeah. So I'll ask you, Ms. Hughes, what can we conclude, if anything, about the relationship between soft drinks and polio? And specifically, can we say that soft drinks cause polio?
We can't say that soft drinks cause polio. We can say that they have a positive correlation, that they move together. But when I poll classes on this question, we brainstorm what could be the possible reasons why. You know, on weeks where soft drink consumption goes up, the incidence of polio goes up. And they were like, well, maybe there's an ingredient in soft drinks that maybe the carbonation, maybe the sugar, maybe something that makes polio more virulent. Or maybe it's that when you have polio, you have weird cravings. You know, like some viruses make, like rabid dogs become really thirsty. And so maybe it works the other way. Maybe it's actually that the polio makes them thirsty and makes them crave the soft drinks. And you can brainstorm all kinds of other things. But it turns out actually that increased temperature and humidity make polio more infectious. And the reason that is that when you're in an environment with increased humidity, you make less mucus in your mucous membranes in your nose and your nasal passages. And so increased temperature and humidity make polio more infectious because you don't have as much mucus to trap the virus. But also, very humid and hot days make people purchase more soda.
Yes. Okay.
Because they find it more refreshing. So in fact, it's a third thing that's completely separate from these two that causes both of them.
Yeah, and so that's one of the interesting findings here that we're going to talk about in more detail throughout this lesson is that, sometimes just because two things are correlated doesn't necessarily mean that one causes the other. And we need a very special type of statistics to tackle cause and effect relationships. And we're going to discuss that as we go. But these are causal relationships in that, there's some correlation going on between. So this is an example of two things that are correlated but that don't necessarily cause one another.
Yeah.
Okay.
Yeah.
Here's another example. For a sample of American men aged 18 to 54, what would you expect the correlation to be between income and blood pressure?
Well, and again, when you ask a class, what do you think between age 18 and 54? Do you think as income goes up, blood pressure goes up? Do you think as income goes up, blood pressure goes down? Maybe you have more money, so now you have fewer stresses in life. Some people say as income goes up, it means you have a more stressful job, so then blood pressure might go up. Other people might say, well, if you have high blood pressure, maybe you're a type A person, and maybe you thrive on stressful environments, so then that other characteristic might cause you to choose jobs that get you higher incomes. So there seems to be a positive correlation between blood pressure and income. The question is, does one cause the other, or should there be some other explanation altogether, right?
So could higher paying jobs cause an increase in blood pressure? Higher paying jobs, maybe they're more stressful.
Yeah.
Could people with high blood pressure be drawn to higher paying jobs?
Type A, hardworking, they don't sleep much, they work, right?
Exactly. But there's another factor here, age, right, which is really one of the first things that we mentioned that's positively correlated with both income and blood pressure, is that as you age, again, between 18 and 54, in general, your income increases. And also, in general, your blood pressure over that time increases. So this is another factor that needs to be played in here. So again, we can't necessarily say that because there's a positive correlation, the one causes the other. We know that they're related, and we know how they're related, but we don't know if one causes the other.
Yeah.
So all this is pointing to this magical little box here that says correlation does not necessarily imply causation.
And we have emphasized this in previous lessons, that just because the R value is high, whether it's positive or negative, that there's a strong linear correlation doesn't mean that one causes the other.
Exactly.
And we've gone over and over this, and we're just going to keep repeating it because it's so critical. But correlations can result from other things.
Yes, and you will see, there will be a question on your test or on, in your textbook. And it will give you this really convincing description, just like the polio vaccine question or just like the blood pressure question. It'll be a really convincing thing, and it'll say, based on what you have seen here, is this a cause and effect relationship? And I would say in the time that I've been teaching this course, which is for a while now, probably about 50% of my students overall always say, yes, sure, this is a cause and effect relationship. But the one thing we come back to over and over again is that really, unless we're in a very specific kind of area that we're going to talk about in a few minutes, correlations, just because there's a correlation, we can't necessarily say that there's a cause and effect relationship between the two.
That's right. And when you do your stat summative, where you choose the variables and you test the strength of the relationship between them, and if you find that there is a strong correlation between your two variables, then your job will be to speculate as to some of the different types of causes, common cause, reverse cause and effect, accidental, presumed, and because you won't be able to say for sure it is cause and effect.
Yeah. So at this point, let's go through each of these different factors and different relationships and find some examples of each.
Yeah.
So a cause and effect.
So cause and effect relationship, it supports your hypothesis that your independent variable causes the dependent variable or is responsible for changes in the dependent variable. And so just as we predicted by our hypothesis, a change in X, whatever it is, your independent, causes a change in Y.
Okay. Before we move on, one thing that we should say about a cause and effect relationship is that if you are to prove a cause and effect relationship, you do that through experiment. Yeah. And it's the only way really that we can claim a cause and effect relationship is that if we've shown experimentally and systematically that this thing causes this thing, when we control for different variables and everything like that, and we can really narrow down. Statistics alone can't ever give us a cause and effect relationship. No. Experiment can give us a cause and effect relationship.
Right. We have to control for all the other things that we think might be that third thing, that age, that humidity.
Yes.
All those things. If we could control for everything else and the only thing we're changing is the independent variable, then any changes in the dependent can be attributed to it. So, and we're going to look at experimental design.
In a few moments. So that's cause and effect. So that's the first one. A common cause factor is very similar to what we said for the blood pressure. Some external variable causes X and Y to change in the same way, right? So with blood pressure increases with age.
Income increases
with age. Yeah. Age is the external variable that causes both to change.
Yeah.
This was also true of the example that we said way back in lesson 1 where you got ice cream sales and crime
rate.
Both of those things are positively correlated, that when ice cream sales go up, crime goes up. And we talked about that and we said, oh yeah, but what's the one linking external variable that causes them both to go up?
Seasonal temperature.
Seasonal temperature.
Yeah.
When it's cold outside, crime rate is lower, and ice cream sales are of course lower. And when it's hot outside, ice cream sales are higher, crime is higher.
Now, reverse cause and effect relationships are relationships where instead of your independent variable causing your dependent, where X causes the change in Y, it actually turns out that it's your changes in your dependent variable that lead to changes in your independent variable. So that what you would end up doing is changing the axes labels, right?
And again, because this is cause and effect, this is something basically that we would prove through
experimentation,
and it would be that exactly our hypothesis was just flipped. Is that, oh no, changes in X don't cause changes in Y. It's actually the opposite of that, is that changes in Y cause changes in X. And so that is, of course, important, but this, again, is a cause and effect relationship that can only be verified
through experimentation.
And
it can be speculated on. Like we said, when you do this project and you find there's a correlation, you could speculate perhaps it's a cause and effect if this causes this. It could also perhaps be a reverse cause and effect. So you can speculate on it, but you can never prove it until you do the experiment itself, right? Now, the fourth kind that we're going to look at are these accidental relationships. And these they're just coincidence, right? That a correlation without any parent causation is coincidence. It could be like, well, just because inflation is going up, that's the reason why everything's getting more expensive. Or, it could just be like butter sales go up with motorcycle sales. Or like, who knows why that is. But if we can't see a cause and effect relationship, reverse cause and effect, or common cause relationship, then it could just be coincidence.
A complete accidental relationship. A presumed relationship is something a little bit more in-depth than something that's completely accidental. A presumed relationship is a correlation where it doesn't seem to be an accident, but it would be difficult to find or to prove a clear common cause or cause and effect relationship. So it's something where, okay, we know something's going on. There's something fishy going on here, but it would take more study and it would be more difficult to find or to prove something that's a clear common cause.
And an example of that would be students who are active in student council and other sports and other activities at school tend to have higher grades. And is it that being more active gets you the higher grades? Is it that having higher grades makes you more active? Is it that your personality predisposes you to be the kind of person who would work harder?
It would be difficult to prove that. But of course, we would presume that there's a relationship there. And so of course that would be something that would be included in future work or the next steps of your study.
So it's not an accident, but we can't exactly figure out what's causing what.
With what we have access to right now, we might not be able to prove it. Okay, so here's a third example for today. Let's classify the following relationships. So in part A, the rate of a chemical reaction increases with temperature.
So if you were to hypothesize what kind of relationship that might be, cause and effect, reverse cause and effect, presumed, accidental, or common cause.
You could create an experiment
to test this.
And
those of you who've taken grade 9 and 10 science probably know that this is a cause and effect relationship, that as you increase the temperature, the rate of reaction goes up because the molecules are moving faster. And so this is a cause and effect. It's not that chemical reaction increases as a result of temperature decreases. We can see that, when this goes up, the other one goes up. So this is clear cause and effect. We chose this mostly because you've already observed this experimentally in your grade 9 and 10 science classes.
Leadership ability has a positive correlation with academic achievement. So you're a gifted leader, or you're high on a leadership spectrum of some kind, and that has a positive correlation with your academic achievement. Okay, so what's going on here? Again, this would be presumed. This would be difficult to prove which one causes the other, or what might be a common cause factor. But we could say, oh no, there's something that's going on here, because statistics will tell us time and time and time again is that leaders and academic achievement, or leadership ability and academic achievement, certainly are positively correlated
with one another.
This one
this is the one.
You gave this one
I gave this one away. The prices of motorcycles and butter have a strong positive correlation. Now, you could go with a few different things on this.
You could.
You really could.
So you could say accidental.
You could say accidental. You could say it happens to be a coincidence that motorcycle prices and butter prices. Some people will say, well, because butter and motorcycles have to be transported and the price of gas is going up,
Yeah.
that that these costs will be going up together. You could say maybe it's inflation, so it could be
Yeah,
common
and I was
cause.
going to say that in general, if we're talking about prices of A and prices of B, over time, both of those things are going up. Now we're talking about prices.
Yeah.
So when you're comparing the price of two different things, because they're both units of dollars, right, or units of cents, or whatever you have, in general, that's a giveaway that you might be able to link these two things
Yeah.
through inflation, because the prices of everything goes
Goes
up,
up. Yeah.
right?
Yeah. Well, yeah. Over time, the
Over
general
time,
trend.
over
Yeah.
time, yeah.
And so this could be a common cause of
Yes,
inflation.
yeah,
This could be, could be just coincidence. If it's happening over a short period of time,
yeah.
it could just be
So if this was
coincidence.
the prices of motorcycles,
Over 30
and
years.
over 30 years, and the sale of butter,
Mm-hmm.
or the number of cubic meters of butter that have been sold over the years, you might say then it would be an accidental relationship. But again, you might say, well, inflation, you could make an argument for some other common cause that,
Yeah.
oh, maybe inflation has to do with it, or
Yeah, cost of gas, whatever, right? But
Yeah.
yeah, you could make different arguments here.
Okay, so here's D. The sales of cell phones had a strong negative correlation with ozone levels in the atmosphere over the past decade. So sales of cell phones have gone way up. Ozone levels have gone way down. Right? So the level of ozone in our atmosphere,
Yep.
In the past decade, sales of phones. Right?
So then the question is there something about manufacturing cell phones or buying or selling cell phones that has changed the ozone levels for the better? And some people, if you really dug into it, maybe you could find something there. But on first glance, it kind of looks like they don't have a lot to do with each other. And in fact, the manufacture, purchase, and sales of cell phones should probably have a positive correlation with ozone levels, considering their transport and other things like
Yeah.
that. So this one here is something where unless you really dug into it a lot, you might say this could be a coincidence that selling cell phones and dropping ozone levels,
Yeah.
one isn't causing the other.
Yeah.
And so it's probably just coincidence.
Now, other students that I've had have said, okay, well, if you look at this, you say, okay, well, cell phone sales have gone way up, with our interest in technology, and really as our population has continued to swell, and North America industrialization, et cetera, et cetera. And the ozone layer has started to decrease significantly, which has to do with population going up and industrialization in North America. And so some people could argue very convincingly that this is not a coincidence, that there was some common cause factor.
Yeah.
But again, whatever answer you take, the important thing is that, okay, you're starting to think about some of those connections. Traffic congestion has a strong correlation with the number of urban expressways. And this one I really like, because
this is a great one.
In Waterloo region, traffic congestion has been increasing year after year after year, for the last number of years. But the number of urban expressways that we've added, and the work that we've done on the expressway in town and all these things, that keeps on going up. Like the number of dollars that we spend, and even if you look in Toronto and adding the 407 and all these things, traffic congestion is still going up, even though we keep on adding more highways and expressways.
Yeah. Now this is like a chicken and an egg kind of scenario.
Yes, yeah.
Because on one hand, if you build it, they will come. Right?
Yes,
so
exactly.
If you put an expressway there, people will be like,
great,
let's use that expressway. So then the congestion increases. If you have a lot of congestion, then urban engineers, and planners are going to say, we need to address this problem. But
So this is probably one of those examples where I would say, oh, well, this is, this could be very likely a cause and effect or a reverse cause and effect type of relationship. And for exactly the reasons that you have kind of said, the thing is that we could look at cities across the world and try and use an ex post facto study to kind of investigate the different directions that different cities have gone. Because we have public transit that is not bad and getting better, whereas other cities around the world have far superior public transit. So all these kind of things add in. But this is one of those, exactly as you said, a chicken and an egg type of scenario.
Yeah, yeah.
Okay, so we'll talk just briefly about extraneous variables. And extraneous variables are really, things that are going to get in our way. They're things that are really going to get in our way. So we've talked about a variety of causal relationships. We've looked at cause and effect, common cause factors, reverse cause and effect, accidental, presume. And we've noticed that several types of relationships might be involved in the same situation. Okay?
Yep.
So we really do have to consider extraneous variables.
They're also called confounding factors.
Yeah.
And if you want to think of these extraneous variables, think of them as the variables you would have to control if you were designing an experiment. These are variables that you'd have to keep the same across all your population or your sample if you wanted to do this. Okay, so extraneous variables are variables that affect or obscure. So they could increase the appearance of a relationship, or they could completely obscure a real relationship because of their effects, right? So between the independent and dependent variable, they're the ones that you'd want to control for if you were designing an experiment.
So if you think about a typical grade 7 or grade 8 experiment that you do in the classroom about looking at independent and dependent variables between plant growth, which would be of course a dependent variable, and all the different factors that affect plant growth, the number of hours of sunlight, the amount of water you give it, whether you fertilize the soil, etc., etc., etc. If you're testing for one of those specific independent variables, let's say the hours of sunlight, but you don't control for how much water you give them, i.e. you give them different amounts of water, that is an extraneous variable that will not allow you to observe a true relationship between the number of hours of sunlight and the growth of the plant.
Yeah. All right, so let's look at an example. You'd expect there to be a strong positive correlation between your midterm mark and your final mark for this course. You assume that a high mark at midterm would likely lead to a higher mark at final. What are some of the possible extraneous variables that could affect this relationship?
Yes, okay.
And so again, when we brainstorm with our classes, what are some things that could get in the way of this midterm and final mark being correlated? We get things where, well, maybe the course itself is designed where the first half is easier or more challenging than the second half, and so then you can't predict the final from the midterm. We could look at, sometimes you get students who have personal issues that could affect the first and second term differently. Personal issues or things like getting your university acceptance letter.
Yeah, and that's something that's very interesting. In second semester, this correlation doesn't exist as much as in first semester. In first semester, this correlation is strong and positive.
Yeah.
In second semester, the correlation is not as strong, and that's because once midterm marks go in to colleges and universities, we still have a whole second half of the course that for some reason just doesn't seem to matter as much.
Motivate them as much.
Once those university marks go in. And so, that's a major extraneous variable.
Yes. The other thing too, because final exam is worth 20%, some people who have test anxiety, and there are a lot of projects throughout the course, so that these projects help you achieve a mark that you can learn the material at your own pace and get help and everything else. And test anxiety could negatively impact your final mark because it includes a big test. A big sit-down test right at the end, which you don't have at midterm. You don't have a major midterm exam.
No, not in this course. And one of those things that like there's probably other reasons right now that you could list off that are probably all very, very accurate extraneous variables, because there's tons of things that could affect your performance.
Yeah.
But again, if you're thinking along these lines, that's a very good thing.
Yeah.
All right, so now we're going to shift gears a little bit, and we've talked about different variables, we've talked about different design, now we're going to talk about the experimental design. So really, what we would like to do is we'd like to say, okay, if two things are correlated, ideally what we'd like to say is that, this independent variable causes this dependent variable to change. Yeah. And the only way really we can get it cause and effect, or we can get it proving cause and effect, is to consider an experimental design. Okay, and there's all kinds. You have to understand that when it comes to statistics, we're really just scratching the surface of what of really this whole field of studies.
You will take courses on experimental design
Yeah.
at university.
Yeah,
Like
exactly.
whole courses. And we're going to spend 10 minutes on it.
And we're going to
right?
spend
Yeah.
maybe 10 minutes. So, but really, if we want to get at cause and effect, we need to do an experiment. And that means we got to control for all the extraneous variables. So
Yep.
here we go.
Yep.
An experimental group is a group for which the independent variable is changed in an experiment or study. So it's the independent variable is what we as the experimenter control. We change the amount of the independent variable
Yeah.
that is administered, and we measure, of course,
the change
in the dependent variable.
Yeah.
A control group then is a group for which the independent variable is held constant in an experiment or in a study.
Yeah. So they're controlled. We use them to check and see if the changes in the X did cause the changes in Y as predicted.
So really then, if we now compare these two groups, and there are changes that result in the experimental group, and there are not changes that exist in the control group, and everything else has been taken into consideration, then we can say that the difference between outcomes is related to the administration of an independent variable.
That's right. And even selecting these groups, the experimental and control groups, if you're choosing a sample from a population, again, you can take a whole course learning how to select these because you want them to be the same age, the same gender, same income, same socioeconomic stuff. Like, list goes on and on and on. So even just choosing how to split your sample into two halves, the half you're going to change things on and the half you're not going to, even that is a major decision as well. Yeah.
Okay, so here's an example. A medical researcher.
Okay, so let's say you want to test a new drug believed to help smokers overcome the addictive effects of nicotine. 50 people who want to quit smoking, okay, so they all have the same motivation, volunteer for the study. The researcher carefully divides the volunteers into two groups, each with, and here's where there would be a lot of decision making, equal number of moderate and heavy smokers. You might have to consider how long they've been smoking for, how many packs a day they smoke, all kinds of other factors, age, everything else. One group is given the nicotine patches that also contain the new drug, while the other group just uses the ordinary nicotine patches without the addition of the drug. So 14 people in the first group quit smoking, and 9 people in the second group quit smoking.
Okay, so 14 out of 25, and then compared to 9 out of 25.
Yep.
All right. So this example is now in 3 parts. Identify the experimental group, the control group, the independent variable, and the dependent variable.
Yeah, and then the second part, can the researcher conclude that the new drug is effective? And the third part would be, what further study should the researchers do?
Yeah, so this will be more of a discussion, and this is a discussion type question. So let's kind of go on here. The experimental group in this study would be the group that receives the new drug.
The new drug, right?
Okay, so the volunteers that were given the nicotine patches with the new drug. The control group then would be?
The ones given the ordinary nicotine patches that did not have the new drug included.
Okay. So the independent variable is basically the presence of the new drug.
Yep.
So is it there or is it not there?
Yep.
The dependent variable is basically the rate of smoking cessation. So how many
quit smoking
in each of the groups.
Yeah. So we're making the hypothesis that the presence of the new drug should cause an increase in the rate of smoking cessation. We're hoping that it will cause more people to quit smoking.
Okay. So conclusions. So what can we conclude from this study? So first of all is that the preliminary results look good. Now, we're going to talk about what looking good means as far as statistics go in a minute. But basically, all we can say at this point is in this sample, nicotine patches with the new drug seem to be more effective than ordinary nicotine patches. And that's because 14 out of 25 quit when they had the new drug, 9 out of 25 quit without the new drug.
We also want to note the fact that this is a very small sample size. So 50 is a reasonable size, but when you do split it in half and put 25 in each group, that's pretty small.
That's a pretty small sample, yeah.
And especially for how many extraneous variables there could be involved. Does each person who's quitting smoking, do they have a supportive partner at home? Does their spouse smoke? Does anybody else in their house smoke? Like all the different extraneous variables, anything you could think of that might affect whether a person quits smoking or not. Stress, jobs, like tragedies in their lives. You would need a lot more trials, and you would really need to look at all the extraneous variables
Yes.
and ask more questions about what's being controlled before any conclusions can be drawn.
All right, so just quickly, let's talk about what looking good, if these results look good, what does that mean? There is an entire branch of statistics beyond anything that we're going to do in this course that's really kind of called inferential statistics. And it means that, we're going to look at the data that we get from different experiments or different correlations, et cetera, and we try and make inferences or predictions about the population and what this means. So if we say that these preliminary statistics look good, well, how good is good? And as you will learn in other courses well beyond this into university, is that really we kind of say in statistics, if you want to say something looks good, it has to reach, a certain bar. It has to, kind of, when we compare 14 out of 25 to 9 out of 25, we have to hit a certain target. And we have to say, okay, well, is the difference in those two numbers good enough to say that it's effective? And there's all kinds of very heavy mathematics and very heavy kind of discussion and appreciation pieces that we could do. So when we say this looks good, this one little phrase right here, preliminary results look good, is really the start of a whole other branch of statistics, which looks at trying to make predictions about a population, and that's called inferential statistics.
Yeah. And it even takes us, this preliminary results look good, take us to the fact that, okay, so now what we need to do is maybe we need to look at, body masses and look at different dosages. Or higher dosages better. Now, maybe instead of controlling whether they get it or not, we take a group and we split it up into 10 different groups and give them each different dosages and see, so you can take this preliminary smaller sample and say, okay, well, and they'll do this because it's cheaper to start with a smaller sample and say preliminary results look good. Can we have more funding now, please, to increase the sample size and do a little bit more work with it? Right?
Sometimes when you read journal articles about different studies that have been done, especially in the health field, their methods section of those journal articles will be pages and pages and pages long because they're detailing what they've done to control for the different variables. Part C of this is further steps, and we've kind of talked about this a little bit. Should the participants be made aware of which drug is being administered to them?
And the short answer is no, they definitely should not, because knowing that you're getting the new drug may impact the results. It's called the placebo effect, and we're going to look at that in part 3. But knowing that you have or haven't got the drug might change your approach. It might change the way you feel about being in the project, might just change your motivation.
Should the researchers know who's had the drug and who doesn't? And I would say again for this, no. The answer is no, because if I'm a doctor and I've got some vested interest in whether or not this drug works, I could treat patients differently, which could affect the outcome. So you would introduce other variables that could creep in and try and mess up your results.
And without even meaning to, some doctors who don't even have a vested interest but know the person is in might say, "Are you sure you haven't had any additional side effects or reactions?" So even like leading questions and introducing some other kinds of bias, just in the way that the interviews go with their check-ins or their checkups, right?
So then, what's the placebo effect? What's the placebo effect? Okay, so we should talk about double-blind studies before we talk about placebo. Double-blind studies are really the best, the most pure. So if we're talking about experiments, neither the patients nor the doctors / the researchers know who's getting the treatment. And of course, then everything would be coded by a research assistant so that no one knows what's going on. Everything's just all in code.
Everyone who's interacting with the patients and the patients themselves, they're not aware. There's someone who's designed the experiment who is determined who's getting what, but nobody who's actually on the ground floor working together knows who's got what.
All right, so the placebo effect is a simulated treatment that causes a perceived or actual improvement in a medical condition. Now, it doesn't just have to be medical condition, but for this example, this was a medical example. But, a simulated treatment that causes a perceived or actual improvement in a medical condition, like if I've got a headache and, I take a Tylenol for my headache and it makes me feel a little bit better, who's to say that if someone, instead of giving me a Tylenol, gave me
a sugar pill,
and I took that sugar pill and I went and sat down and relaxed, and then I started to feel better. Of course, there's no drug that's been introduced into my system. I think that I've taken something, and so mentally, in this kind of placebo fashion, I end up curing myself of my headache, and
Yes.
I haven't even taken a Tylenol.
And the placebo effect is so powerful that it's actually what we're controlling for when we do double-blind studies.
Yes.
It's sure there may be some bias in the researchers, but also the main thing is that people who think they're getting a powerful drug, they believe that that's happening, and it actually can change their physiology. It
Yes.
can actually lead to improvements
Yeah.
in biological